get back to this aromatics handout. Does anybody have any questions about what we talked about Monday? And it seems like it's Friday. It seems so late. Any questions about what we talked about on Monday dealing with aromatics? We started talking about the reactions, but we didn't get a chance to get into the mechanism. So I'm gonna go through that with the halogenation and the alkylation acylation. We won't do the mechanisms for the nitration and sulfonation. We'll just go through the other three. All right. So let's take this reaction right here. And again, we're looking at electrophilic aromatic substitution. In other words, you're adding an electrophile to the ring. Oh, it's too thin. So electrophilic aromatic substitution. All right, and I said it on Monday. The way this works is you have a step where you prepare your electrophile. You have a step where the nucleophile, which is the ring, you attach the electrophile, and then you have a step where you reestablish the aromaticity. So in this case, this is one of the purposes of having a catalyst, right? So it's the catalyst that helps to facilitate that electrophile activation. So it's going to facilitate the activation of your electrophile. So let's look at the mechanism and look at how it works. All right, so of course, in the first step, you will have, I'm just going to say E plus activation. Right, so the bromine is here. Go ahead, if you have a question. And then your iron bromide is here. Right, so what happens in this case is your bromine actually uses a pair of electrons to form a complex with that iron bromide. And I didn't know we were gonna get a concert today. All right, so this is going to form a complex where now your bromine is here, one of them. Right, and you have a so you basically chelate the bromine to the iron, right? Iron is a transition metal. It's got a bunch of empty d orbitals. Well, not a bunch, but it has empty d orbitals that can accept electrons. So you get this iron bromide complex. Right. So whenever you have a non-metal with lone pairs that can coordinate to a metal, we call that a complexation. All right. So these things complex. And so once that happens, this bromine, even though it has 3 lone pairs around it, there's a dipole in this direction. So this bromine becomes partially positive. So that's when the ring in step 2 can attack. So let me show that part. So in this in this case, your ring is a nucleophile, right? So here now you have your ring here. I'm just going to draw it out like that, and it'll be, we're going to use that pi bond. All the pi bonds are equally reactive, but we're going to use that one. So it'll be that plus this complex. Sorry. Right, so now this is going to attack here. And again, without the catalyst, this doesn't happen because bromine is really too electron rich to accept a pair of electrons. But the fact that the iron is there and you have that dipole towards iron, towards that metal, is sucking all the electron density that way, it makes that bromine more susceptible to nucleophilic attack. So once that happens, right, now you've added bromine to the ring. I'm just going to put it up here. There's still a hydrogen here. There's still a hydrogen here and a plus charge because you broke that double bond. And then that's plus FeBr4. And now this is an anion. That's negative. Right? So once you attack the bromine with the nucleophile, with the ring acting as a nucleophile, then you generate this intermediate. And this is the problem. This getting to this part right here is why this reaction requires a catalyst, because you're going to have to, the ring is no longer aromatic, so you lose a lot of energy, right? So this is what's called this intermediate, and it's common in every one of these reactions. This intermediate is going to be common. This is what we call an arenium ion. All right.
My love is blind. Can you see my?
All right. Once you get to that, this is the final step is to do what? I gave 3 steps on Monday. You activate your electrophile, you attack the electrophile with the ring, and then what's the final step? All right. Final step is to reestablish aromaticity. And it's going to happen with everything that's already present. So I have my rhenium ion. And then the iron species that I generated up here, that's actually going to act as a base, and it's going to come in and do an elimination. So now all that energy that we lost by breaking up the aromaticity, we get it back. If this doesn't happen, the reaction won't go. So you always want to have a step where you reestablish that, and then you end up with this HBr, and then your catalyst. The catalyst never gets used up, right? It's always going to be regenerated at the end of the reaction cycle. right? Never anytime you do a reaction with a catalyst, you always regenerate it at the end, right? Because it's not a reactant. It doesn't react. It takes place in the reaction. It facilitates the reaction, but it doesn't actually react. It always gets regenerated. All right, questions about that? All right, I think what I want to do for the we're gonna do that one. For the acylation, we'll walk through that one. And for the alkylation, we're gonna actually work one of the examples down at the bottom. All right. Any questions? Every time I ask that, I already know what the outcome is, but I'm asking anyway. All right. So let's look at the acylation reaction. Actually, I'm gonna take one of these from down here. I'll take this one. We don't have to predict the products because we're gonna go through the actual mechanism. Right, so this is what we call a Friedel-Crafts acylation. And it's an acylation because we're going to add this carbonyl group right here to the ring. Right, when you add a carbonyl like that, it's called an acylation. Same thing like, which reaction did we do? I can't remember. I'm drawing a blank. Anyway, I'll come back to it. But the product of this reaction is here, right? So I add this entire functional group in to the ring. All right. Let's look at how that happens. Notice that there's a different catalyst here. The catalyst is aluminum trichloride. Any reaction you do on an aromatic system has to be done with a catalyst. Otherwise, it won't go because the aromatic ring is too stable to react under normal conditions. So you have to make the conditions conducive to its reaction. And you do that by adding in a catalyst. Right, so what's the first step? What was the first step in the reaction that we showed above? Just like the reaction above, the first step is electrophile activation. I don't even know. And the electrophile is obviously going to be your acyl group. So this is, I'm going to write it like this. There's a difference here, unlike you're still going to get the complexation, but rather than the complex getting attacked by the nucleophile, you'll have a cation. So this is still going to complex with aluminum, right? And you're actually going to break this bond right here. So you end up with a cation here plus AlCl4, and that's minus. That's negative, right? The cation can do resonance to stabilize itself. So the oxygen can push that pair of electrons there and you can do resonance. So you end up here. Right? Either one of these species can react with the nucleophile, with the ring. So we're just gonna show show this one. So this is now, I have my ring here. I'm gonna keep the keep the pi bonds in the ring the same. So just to keep track of the atoms. Right, so that's that plus that. And then of course the ring will attack the carbon. That is a carbon right there. So now you're going to end up with still with an uranium ion. With a plus charge here. And then this is not the reestablishing aromaticity is not something new, right? It's just an elimination reaction. It's like a E1 type of elimination where you got a positive charge adjacent to an alpha proton. So that's the third step is to reestablish aromaticity. And then the same way, like above, you had that the iron bromide complex that acted as your base. It'd be the same thing here, but it's with the aluminum. Right, so this is going to act as a base to do elimination. And then reestablish aromaticity and get your products. So the second step is the same as up top to nucleophilic attack. All right, so the other reaction that I want to look at is the Friedel-Crafts alkylation. And we're going to take an example from here. All right, so if you look at the question, Friedel-Crafts alkylation is carried out with a primary alkyl halide. Sometimes unexpected products are formed. You can already kind of see where the question is going. If you look at the product, it's not the expected product. The expected product would look like this. Carbons in that chain. Right, so it's the expected product, but it's not observed. What you do observe is the actual reaction taking place at this carbon right here. So obviously, if that's the case, then something had to happen, right? Something had to happen. And so let's look at this particular reaction because it goes through a similar mechanism to the acylation. It goes through a carbocation intermediate. So let's look at that. First step, same as above, right? Preparation of your electrophile or activation. Of the electrophile. And again, with iron bromide, it's going to be the same. You're going to get a complex. Right, this is going to form a complex with the iron bromide, and then eventually, right, that carbon bromine bond is going to be broken. So you end up with a that's right, primary carbocation. Right, primary carbocation, which you know is bad, right? This is an unstable cation, right? But we also have a tertiary carbon nearby that has a hydrogen that if we shifted it through a rearrangement, we could get a tertiary carbocation. So one of the things about the Friedel-Crafts alkylation, which this is an example of, is that sometimes you get these rearrangements and you get these unexpected products simply because sometimes you may make a carbocation that is unstable, right? So this happens. We've seen this before, where you have a hydride shift, and then once that hydride shift takes place, you get a new, more stable carbocation. Now the carbocation is here, right? And that is what ends up reacting with your ring. So now in the second step, where you have nucleophilic attack of your ring, that's the cation that's going to get attacked. Right, so you attack here, and then you'll get the same. The mechanism doesn't change. You get the same rhenium ion intermediate, just with a different substituent attached to it. So now this is here. We got a plus charge here. Right, and then once you, and this is obviously set up now to do elimination. So you want to reestablish, and this is the key step. Nothing changes. It happens just like it happened in the previous step or the previous reactions, whatever that catalyst. Whatever the identity of the catalyst was after it adds the halogen or whatever you're adding to it, that's going to come back and do your elimination. And in doing so, you do three things. You reestablish aromaticity. So your aromaticity is now reestablished. And then you also regenerate the catalyst. and you generate one molecule of, in this case, HCl, because it's the hydrogen from the ring that ends up with one of the chlorine from that. Oh, I used the wrong one. So this should be FeBr4. Sorry, let me erase that. Same, but the same thing happens, right? You over here, you regenerate FeBr3, and you get a molecule of HBr. Right, so the alkylation is, again, you can add different functional groups to the ring. For acylation, you're adding a carbonyl. Right, by starting with an acid chloride as your start material. And then you have for the alkylation, you start with an alkyl halide, and you end up with a alkyl substituted ring. So alkylation is going to add an alkyl group. And then just like halogenation, you're going to add a halogen. Right? We've already talked about that, but I'll just write it up here. Right. So those are the three main mechanisms and main reactions for aromatics. You can look up the mechanisms for the nitration and sulfonation. Right. And the other thing I want to talk about today are the directing effects. So over here, well, not necessarily direct effects yet, but I want to talk about mono and disubstituted benzene. So this is, if the benzene already has a substituent on it, we call it monosubstituted. Right, that ring, if I add another group, right, whether it's adjacent to it like this, here, or here, it changes. Number one, it changes the substitution pattern. These are all disubstituted, meaning they have two substituents. Right, and then the way we think about this, normally if the initial substituent is here, we'll call this will be 1, and then this is 2, that's 3, and that's 4. But when you have a disubstituted benzene ring, you don't use numbers. You use terminology. So the term here, if it's a 1,2 substituted, then we call that ortho. The meta would be 1,3 substituted, right? If they are in a position like a 1-3 position like shown here, then we call that meta. And if they are if the relationship between the two substituents is a 1-4 relationship, then that's called para. So ortho, meta, and para. And we only use that for disubstituted benzene rings. So ortho, meta, and para only used to describe disubstituted benzene rings. Right, you don't use it if the ring is tri-substituted. You don't use it if it's mono-substituted. But if it's disubstituted, then you have to use this convention, right? So some examples are down here where you have ortho chloroanisole, right? So anisole is the parent. Right, so this is anisole right here. That's a common name. It's a common aromatic compound. It has a methoxy group attached to the ring. And so since that's the parent, the chlorine is a substituent. And because they are in a 1-2 relationship, that means that you're going to use the prefix ortho. So it's ortho chloroanisole. Over here, same thing. This is the parent anisole. Right, but because the two substituents or the two groups are in a 1-3 relationship, we call it meta. So that's they're in a meta relationship. So it is meta chloroanisole. It's always, and this goes back to organic 1 when we did nomenclature. It's always the prefix, right? The parent is always last. And then the substituents are always listed prior to the parent. All right, so here, same relationship. This is 1-4. So it's para, right? 1-4 is para, 1-3 is meta, 1-2 is ortho. So parachloroanisole. This R, let me actually fix that because that should be a methoxy. Right, parent is here. And then the X, I need to fix that too. So chlorine. Is here. So parachloroanisole. So ortho, meta, and para. It's important to know these positions because that leads to another part of the discussion about directing effects. So when you do a reaction on a substituted benzene ring, right, there are directing effects based on what's attached to the ring. So anytime you do a reaction on a substituted ring, mono-substituted, right? You're gonna that reaction is going to be dictated by what we call directing effects. So if there's a donor on the ring like this methoxy, it can donate into the ring by resonance. And we indicate that by just using DON for donor, right? If it can donate into the ring either through resonance or through induction, that's gonna, so donors are ortho para directors, right? So anything you add to that ring is gonna have to either add here or here. And you can see, and so over here, you get to actually get two products. You get the para product, where bromine is at the 4 position, and you get the ortho product with bromine at the 2 position. And the para is usually favored. And so para is usually favored due to sterics, excuse me, due to sterics, right? You can see in the para position, the 2 substituents are further apart, which is always good because that means there's less steric interaction between them. So para is normally favored if you have to choose between and you can see because you got competitive products, 2 products are formed, that you have, you're going to have a product distribution. You're going to get percentages and a ratio of each product to the whole, so on and so forth. So the para is favored, or the major product, because of sterics. If you have a electron withdrawing group on the ring, and that literally means you can take electrons from the ring through resonance like that, in this case. And you can, so this is what we call an electron withdrawing group. Remember, you can put electrons in either through resonance or induction. And the same with electron withdrawing groups, right? It's either by resonance or induction. All right, it's going to be either through resonance or induction. Examples of donors, just like I showed up top, the methoxy. Actually, let me just move this down and I can put them underneath. So methoxy is a donor, excellent donor. You can have if you have an amine attached, like a nitrogen attached, that's a donor. You can, if you have a CH3, that's a donor through induction, not resonance, because it doesn't have any electrons to give. Right? You can have a halogen. Even though we know halogens are typically electron withdrawing because of their electronegativity, when you put a halogen on an aromatic ring, it actually acts as a donor. Same thing here with electron withdrawing groups. You can have like a nitro group. You can have carbonyl attached to the ring. You can have a pi bond attached to the ring, a nitrile, right? This carbon is partially positive, so it can accept a pair of electrons, or it can, and it's also sp hybridized, so it's also electron withdrawing through induction as well. Mm-hmm. So this can do induction or resonance. All right. So those directing effects matter, right? Anytime you have a ring that's already substituted, what's on the ring is going to determine what your products are. So down here, if you have an electron withdrawing group on the ring or an acceptor on the ring, that's a meta director. right? So that activates the meta position. And then donors activate ortho-para positions, right? So here where it says over here, electron donating groups are ortho-para directors. That means those positions are activated. And then where it says here, electron withdrawing groups are meta directors. That means though that position is activated based on what's attached to the ring. And it's fairly, for the donors, if you look at what the resonance forms look like, you'll see immediately if the ring is acting as a nucleophile, right? Then that means that if you're adding electrons to a site, that's going to make it more nucleophilic. So if we take this with the methoxy group attached to it, right, and look at the and examine the resonance forms, you can see right away if the ring is going to be a nucleophile. That means you need electrons wherever you're trying to add your electrophile. Right, so the ortho, this is ortho, and you can see that that site is activated. It's para electrons there. So if you're going to add an electrophile, you would want to add it here, because this is electrophilic aromatic substitution. And then if you draw the next resonance form, you're going to see the para position get activated, right? All through resonance. So I can draw this resonance form. And then I got a pair of electrons here. So now that's activated. Right, so that's activated to attack an electrophile. So that's where your electrophile is going to add, because it's electrophilic aromatic substitution. So you're adding an electrophile to the ring. Right, the same with the acceptor. It's just two benzaldehyde. If you look here, the acceptor is pulling electrons out of the ring, and then what you'll notice right away, now that ortho position is positive. You cannot add an electron, you cannot add an electrophile there because there are no electrons to give to the electrophile. Right, and then if you draw the next resonance form, right, push these electrons here, you can see right away that's going to be a positive charge at the para position. So you can see right here, the para position is deactivated. Right, you can't add an electrophile there. Just like you can't add it at the ortho position. So the position that's activated in both cases is meta. If you look right here, this is meta to where that group is. So the meta position has electrons there and here. All right, we're gonna stop here. We'll pick up on, actually, I think classes are canceled on Friday after 10, but I'll go ahead and cancel ours also. So we won't have class on Friday. All right, have a good one.